guess I am the emissary from the machine learning research community, and as such I want to talk today about algorithmic decision making, kind of many of the topics that came up yesterday, and in particular algorithmic decision making when the algorithm is the result of a machine learning or statistical modeling process. I think what I'm going to talk about today has a very different flavor in the sense that even though a lot of the concerns that I'm going to talk about today are the same as the ones that were being discussed yesterday, what I want to tell you about today is kind of what's going on in the machine learning community. What can you do about these things? Not from a regulatory, legal, or watchdog perspective. I think all of that's very important and interesting and dovetails with what I'm going to talk about, but actually from an algorithmic standpoint. So if we're concerned about social norms in machine learning or algorithmic decision making, whether that social norm is privacy or transparency or fairness or anti-discrimination, there's actually a fairly large body of research that's quite active on endogenizing those social norms in algorithms in a way that gives you, kind of provable guarantees about the behavior of those algorithms. And so I just want to give you today a bit of a snapshot about that research and also just try to maybe demystify machine learning a little bit and talk about, where the problems are when it comes to conflicts with social norms and what you might do about it from an algorithmic perspective. Okay, so, quickly on the heels of machine learning, kind of the buzz about machine learning and deep learning and, tackling these incredibly important problems like detecting kittens in YouTube videos and playing Go against South Korean champions, then comes the buzzkill about the many instances, sort of demonstrable instances in which machine learning or statistical modeling results in measurable discrimination. And so I here just have some, one small sample of the many recent mainstream media articles about cases in which people have shown that machine discrimination, whether it be by gender, by racial group, by age, what have you. And what's interesting about these examples is that they all share this sort of the common concern, and the sort of range of stakes involved is in the variance is huge, right? So it's everything from what ads Google decides to show you, which I think most of us probably don't care that much about, to things like criminal sentencing, which we would all agree the stakes are quite high. And so one of the things, I've spent a lot of time along with colleagues from the computer science community talking, speaking and talking to people in forums like this that are meant to bring regulators together and legal scholars and philosophers with kind of rank and file machine learning researchers. And one thing that I find is helpful is to talk about how can this happen? How is it that discrimination is getting into algorithmic decision making that's the result of a machine learning process? And one of the things that I was sort of surprised by early on, and maybe this is changing since when I first started doing these kinds of things, is that there's this kind of sense amongst, it seems like there's a sense that the actual algorithms, the code that's generating models from data are incredibly opaque, difficult to understand, and complicated. And this slide is meant to demonstrate that nothing could be further from the truth. This is a Wikipedia, this is the pseudocode on the Wikipedia page for stochastic gradient descent. Stochastic gradient descent is basically the algorithm that underlies deep learning in neural networks. And nothing, if you really wrote this out in C++ or Python or whatever you wanted to, it might get twice as long as this, but it wouldn't get 100 times as long. And the basic principle would be the same, and the principles I've kind of highlighted in pink or red here. Nothing could be more basic. It's like for each data point in your training set, look at the error of your current model with respect to the thing you're trying to predict, for instance, whether somebody will repay a loan or not. And to the extent that you have error, update the parameters of your model to decrease the error and repeat this until, you find a good model or you're tired of doing that, okay? And so, if you compare this code, for instance, to the code of, let's say, Grand Theft Auto, this is so simple and has such a basic scientific objective principle underlying it that, this is not explicitly where discrimination arises, right? And when people talk about transparency, which I think is an important topic, I think we would all agree this is incredibly transparent. This is easy to understand. So if we're concerned about transparency and accountability and the like, or discrimination, it's not explicitly here in which those violations of social norms are creeping in. Okay, so where does it happen then? Okay, well, now the answer gets a little more complicated and interesting, and my joke about where unfairness arises is kind of like the old computer science joke about standards, which is the great thing about standards is that there's so many to choose from. So there's many ways in which unfairness can creep into machine learning. So one obvious example is just the data, right? So if you start with data in which there the code that I showed you on the last slide is going to eradicate it, right? And it might even exacerbate it if that is helpful for predictive accuracy. So, I don't think to this audience I need to give the many, many examples you can give of these things. There's sort of negative feedback loops, like in predictive policing. Of course, the more police you put in a neighborhood, the more crime you catch there. And if you're using that as feedback for your model or your data for training, you're going to learn that you should put more police there, even though the actual sort of inherent rate of criminal behavior there may not be higher than somewhere else. Similarly, in college admissions, wealthy applicants might tend to have higher SAT scores because their families can pay for SAT preparation classes and many retakes of the exam, et cetera. And so one thing you could try to do about this that has received some attention is try to correct the bias in the data itself, to sort of be cognizant of these sorts of bias in the data and try to reduce or eradicate them. There's been less attention paid to this, I think, because of the next bullet, which is that it could be that you do that and still bias creeps in the second step, which is in the models, right, the output. So if you think of the data as the input to a machine learning or statistical modeling process, the output is some predictive model like a neural network or a decision tree or a linear regression model, what have you. And here, of course, the concern might be discriminatory treatment of subpopulations, right? That when you look, for instance, at the false rejection rate of loan applicants, that rate differs significantly amongst racial groups, for instance, or across gender or age groups, et cetera, all other things being equal. And there's been a fair amount of research recently that I think is good research, some of it coming from surprising places like Google, trying to design, you sort of try to post-process models with various subpopulation guarantees. So rather than trying to fix the model or the algorithm that produced it, the idea would be to actually look at that model, measure the extent to which it's exhibiting discriminatory behavior on a subgroup, and then try to correct it at that output level. So to kind of demystify this a little bit, most definitions of fairness in statistics admit that would call making random decisions like a lottery a fair decision, right? Because when you're making a random decision, you're not conditioning on anything, so you can't be, discriminatory against one subgroup or another group. So a lot of these kind of post-processing frameworks essentially are doing something like taking a deterministic model that has discriminatory behavior and then mixing it with some kind of probabilistic model that's trying to equalize behavior across groups. Okay, and examples of the types of statistical definitions I'm talking about, which I'll say a little bit more on the next slide, are equality of false positive or false negative rates, type 1 and type 2 errors, or calibration, which is kind of a weaker statistical notion. Now, none of this, of course, addresses the thing between the input and the output, which is the algorithm itself, which is deriving the model, okay? And that learning algorithm might be generating data through its decisions. So a lot of traditional statistical kind of fairness notions kind of think of this model where there's like a train period and then a test period, like a training data, and then you're going to deploy the model, and that's kind of the test period, right? And in a lot of settings, actually, your algorithm itself is dynamically or sequentially generating decisions, okay? And so that kind of framework isn't appropriate. So, for example, in lending decisions, you can go ahead and take historical loan decision data from either a person or an algorithm, but that data always has the property that while you find out whether people you gave a loan repaid that loan or not, you don't find out whether people you didn't give a loan would have repaid if you had given it to them, okay? And this is a significant bias and problem that kind of cannot be corrected by simply the first two methods that I meant. You really need to think about the algorithm's decision-making process in a sequential, dynamic, online way if you want to kind of get at this stronger notion of fairness, okay? And so this is just a little bit about kind of, where the sort of the machine learning pipeline and the different places in that pipeline that discrimination might arise and how you might try to correct it at those various places. And so I and others in the machine learning community are basically kind of in like a little research loop right now, or a research methodology that I think is quite sensible, and I'm going to spend the rest of my time telling you a little bit more about, which is, kind of the only thing to do from a scientific viewpoint about these kinds of issues is to pick a technical definition of fairness, and I'm going to talk about the choices there in the next slide. Pick a technical definition of fairness like equality of false negatives, for instance. Pick a particular learning framework by, I mean, what type of model you're trying to learn and whether you're more in like a batch setting or more of a sequential setting. And then explore the consequences of your choices. Explore the consequences of a particular definition of fairness in a particular learning framework. And by explore the consequences, I mean, the type of thing that computer scientists on the algorithmic end of things do. We try to design algorithms that meet some performance guarantees, in this case, like a fairness guarantee, and then we try to explicitly understand what's optimal, like how far is that algorithm, how much can we understand the extent to which that algorithm is the best possible algorithm we could find for that particular notion of fairness and the particular learning framework we're looking at, and to what extent might improvement be possible. Okay, and I'll say more about this shortly. Okay, so the goal is to sort of understand the inherent costs of fairness, and there are going to be costs, right? It is not the case that you can have perfectly fair models and also maximally predictably accurate models. There's going to be a trade-off, and we have to get used to looking at those trade-offs and making choices about them. Okay. Okay. So what are the different notions of fairness? Okay. So there's many of them, unfortunately, and I'll say a little bit about that unfortunateness in a second. But to just give an example, one very basic, very weak notion of fairness is what's called sometimes statistical parity, which is kind of a merit blind notion of fairness. It would basically say something like, look, whatever rate you're going to give loans to racial group A, you have to give loans to racial group B at the same rate, regardless of creditworthiness. Okay? So this isn't looking at, who deserves a loan or who's a better risk or who's a worse risk. It's just like if you're giving it to 17% of group A, you have to give it to 17% of group B. Okay? More interesting and natural, especially in real settings where there's something at stake, is where you actually want to take merit of some form into account. Okay? So an example would be kind of unbiased treatment at the group level, namely, like the false arrest rate in group A has to be approximately equal to the false arrest rate in group B, or the rate at which you reject people that are creditworthy for loans in group A should be similar in group B. Okay, so now you're actually taking merit into account, and so this is sort of a more satisfying definition of fairness because you're admitting that you want to take creditworthiness into account in making lending decisions and build accurate models that are profitable for the lender, but you're also concerned about fairness, but you're explicitly taking merit into account in both of the subgroups that you're trying to protect. Okay, now that's still kind of cold comfort if you're one of the people that was falsely arrested or incorrectly denied a loan, right? Which this is allowing. So much more recently, people have started to look at algorithms that promise fair treatment actually at the individual level, okay? And the kind of thing I mean here is I would really ask that if a group of people or two applicants have shown up at the same time for a loan, and in reality, ground truth, one of them is actually more creditworthy than the other one, I shouldn't favor the less creditworthy one over the more creditworthy one. I can give them both a loan. I could flip a coin to decide who to give a loan. I could deny both of them loans, but I can't explicitly have a bias in favor of the less creditworthy candidate. Okay, So this is a very strong definition of fairness that you can actually meet under some circumstances, but under, as you can imagine, sort of fewer circumstances than you can the first two types of more statistical definitions of fairness that are permitting you to make mistakes, okay? Now, wouldn't it be nice if there was sort of a single definition of fairness that was, you know, very, very strong and that you could actually algorithmically guarantee while still finding predictively accurate models? Yes, that would be nice. Unfortunately, we already know just from a number of papers in the last few years that there are basically strong tensions or contradictions even between the notions that I've described here. Okay, so there have been a couple of papers in the last 2 years that you could kind of think of as like Arrow's theorems for fairness. Okay, so these papers have the following form. You know, here are 3 properties or axioms about fairness that we can all agree any definition of fairness should meet, okay? And you look at these properties and you say, yes, yes, yes. Any reasonable definition of fairness should meet these properties. These are even too weak. The other properties should also hold as well, but for sure these should. And then, of course, the punchline is, you know, theorem 1, you cannot satisfy all 3 of these properties simultaneously except in, you know, kind of trivial cases that will never apply in the real world. So we already know there's not going to be this single monolithic definition of fairness that we all agree on. There's, you know, if for instance you're trying to get what's called calibration and you're trying to get equality of false positive and false negative rates simultaneously, already there's a theorem that says in general you won't be able to achieve that, okay? So you're going to have to kind of commit to one of these definitions at the expense of other definitions and you know, explore the consequences. So this is an example of not just a trade-off of the quantitative kind, which is like, well, I've chosen I want the quality of false positive rates, and I'm looking at the trade-off between accuracy and fairness. This is like a conceptual trade-off where, you know, if you want one definition of fairness, you are implicitly giving up on other definitions of fairness that you might, you know, also care a lot about. Okay. And one comment I want to make that came up a little bit in one of the talks yesterday, I noticed, is that, you know, again, all these definitions are often applied to the models output by a machine learning process, which you can think of as like the test phase. And it's very important, I think, especially in the modern era, to think about the fairness of the decisions made by the algorithm kind of all along the path, right? Because in reality, this division into a training period and then a test period is kind of a fiction, a historical fiction of the machine learning community in modern times. Because it really is the case that, you know, at large tech companies, for instance, they're perpetually retraining their models, right? Every single time you click on an ad or don't click on an ad at Google, that is implicit feedback about the results that it showed you, that it's immediately incorporating as data into an improvement of the model. If not that very second, then certainly tonight they're going to, you know, update the model. Okay, and so, you know, maybe the most important thing to remember is that there's kind of, you know, no free or no fair lunch. And that we need kind of as a research community and society to get used to looking at pictures like this. So without going into details, this is a plot generated on the well-known Compass criminal recidivism data set. And without going into the details, each little red dot here corresponds to a different statistical or predictive model. And for each such model, I'm showing its predictive error, so lower is better. And I'm showing you its unfairness according to like a standard statistical notion of fairness. And again, lower is better. And so, you know, the first thing to observe here is there's no point down here, right? There's like a Pareto or efficient frontier here of models that I claim you just cannot get off of. You cannot get below this curve. You could do worse, you could be out here, but you can't get into this region. Okay, and so recidivism in criminal sentencing, you need to look at figures like this and decide where you want to be on this curve. You know, you could say that fairness is paramount, and so you want to be over to the left, and then you're going to have very high predictive error. You're going to make a lot of mistakes. Like either a lot of guilty criminals are going to go free, or a lot of innocent people are going to be convicted. Okay, you can choose to be way over there to the right, in which you have a lot of unfairness, but you're much more predictably accurate. You make fewer mistakes, but you're exhibiting racial, but your model is, clearly demonstrating measurable bias, if you like, or different treatment across racial groups. And there's just sort of no way around this. And we sort of need to get used, I think, to talking about figures like this in these sorts of policy debates. Yeah. Yeah, Helen. Yeah.
We can bring a mic over here.
This is just a point of clarification. So so this curve that you produce, it doesn't matter which conception of fairness
this is a plot for a particular definition of privacy that basically asks that similar people be treated similarly.
Yes.
But I promise you that whichever notion of fairness you picked, there'd be a curve like this one, and it would have this same basic shape. Like, the numerical values on the axes might change just because the units are different, for instance. But there's going to be a curve like this. And just to say a little bit more, like every model here is a straight up OLS model. Every point here is a simple linear regression model, and that linear regression model was solved by minimizing some weighted mixture of an error objective and a fairness objective, right? And as you vary the weight, the relative weighting of fairness versus error, you trace out this Pareto curve of optimal models. And in this case, we know that they're like optimal, because like OLS is like one of the few learning problems where you can actually, it's convex, so you can actually find the global minimum. Whereas in general, in neural networks, when you find a neural network that minimizes some objective function, you don't know that there might be a much better model, right? And so, sometimes we're going to be looking at these curves and we won't know that there's not a better curve, but that better curve might be hard to find computationally just because of sort of, computational complexity. Okay. Good. So let me just wrap up by telling you about some very recent work that we've been doing here at Penn. We actually just posted this paper on arXiv a few days ago, and then I'll make some more general comments to wrap up if I've got a few more minutes. So one of the things that we've been doing here at Penn is trying to think about kind of stronger fairness guarantees that still permit tractable algorithms that yield predictive models. And one thing we've been kind of interested in and concerned about lately is what we've called fairness gerrymandering. And the high-level idea of fairness gerrymandering is that I might meet some higher-level coarse fairness constraint by actually subdividing the groups that I'm trying to protect in a way that lets me meet that objective. So let me describe how this might happen in like a deliberate evil way. If I'm an advertiser, for instance, and I'm required to show an ad for my service, for instance, at the same rate to two different racial groups, but I really don't want one of those racial groups to show up and buy my service or join my country club, for instance. Let's say it's a country club, just to sort of, fix ideas. One thing I might do is say like, well, if I have to show this to 25% of, group A and 25% of group B, and I don't really like group B, I'm going to deliberately find the 25% of group B that lives far from the country club and can't afford the membership fees, and that's who I'm going to show it to. And to group A, I'm going to show it to the 25% that are wealthy and live near the club. Okay? And so you look at it and say, look, you asked me to treat these two groups equally in the statistical sense, and I've done it, but I've done it by gerrymandering. I've done it by subdividing the groups into sort of combinatorial subgroups. Okay? And actually, one thing that's interesting is that Facebook has a hate speech policy that kind of has this form. They basically say, well, look, there are these protected attributes like race and gender, and there's a couple of others. I don't think age is not one of them. There's like 4 or 5 different kind of demographic properties that they say are protected. And then they say that not only are those protected, but any combination of them are protected. Okay? So for instance, race is protected and gender is protected, so that means that black women are specifically protected. That means that if you can't kind of get around their hate speech policy by kind of picking a more specific subgroup and say like, oh, well, my hate speech wasn't about black people in general, it was about this complex combination of black people. Okay? And more worrisome than sort of deliberate attempts to do this gerrymandering is the fact that, like everything in machine learning, if you don't design a machine learning algorithm to avoid this kind of gerrymandering, and it's predictively helpful to do it, it will find it. It will do it. Okay. Then this is like a general algorithmic principle. Like if you didn't put something into the explicit objective function that you're optimizing, you shouldn't expect that property to hold in general. Okay. And we've actually, shown, and so this leads to two interesting problems, kind of an auditing problem and a design problem. So given an algorithm that's making decisions, is it, can I actually do this, or can I audit it for this subgroup fairness? Because the problem here is sort of an algorithmic or computational one, right? If there are kind of D attributes that I'm trying to protect, then there's kind of 2 to the D possible combinations of them. And so if D is large, right, I mean, there are many data sets in which the number of protected attributes is actually pretty large because it has to do not just with, basic ones like race and gender, but more complicated ones that might be proxies for that, et cetera. So there's both an auditing problem and also a question of whether you can design an algorithm. Let me just say a little bit about the second thing. So we, kind of figured out an algorithm that actually gives promises of fairness, not just to the sort of top level groups that you define, but to these subgroups. And it has kind of an interesting, appealing form, I think, especially for this audience, because the way you get to this algorithm that gives subgroup fairness is by designing the algorithm as a game between 2 players. One of them is a learner, and the other you can think of as a regulator. And the way this 2-player zero-sum game proceeds is at any given moment, the learner has some model that they tried to optimize for predictive accuracy, and then the regulator audits that model and discovers like a subgroup on which that model exhibits discrimination. And then that subgroup basically gets added as a constraint on the objective function that the learning algorithm is minimizing, and then we go another round, okay? And so there's this back and forth, this is all inside of the code. Inside of the code, there's this loop in which a learning subroutine and a regulator subroutine are kind of fighting with each other, okay? And nicely, the equilibrium of this game turns out to be whatever model is maximally accurate from a predictive sense while meeting the constraint that it's fair on all these subgroups, okay? Okay, so let me just wrap up more generally on, kind of research in the area of machine learning and social norms. And, there's many social norms you can imagine. Many of them were discussed yesterday. I wasn't here for all of yesterday, so I'm not sure if we also got around to things like, morality and ethics. But, there are people in the machine learning community that are thinking seriously about how you might approach these problems, again, from a technical perspective. And just to talk about the possible approaches, I think a lot of the people in this room are experts at, legal and regulatory approaches, which I fully embrace that those are going to be ever more important as we go forward. But I think, it's also important to think about how we can help inside of the algorithms themselves and design the social norms that we care about inside of the algorithms. And one reason I think that's especially important, and this was touched on at least briefly in some of the talks yesterday, is that I think the pure legal regulatory watchdog approach, unfortunately just, as computer science would say, doesn't scale well, right? And if the way that we're going to kind of as humans catch instances of social norm violations or malfeasance by human organizations looking at the behavior of algorithms, just the scale at which these decisions are being made algorithmically these days is going to be extremely difficult to keep up with, right? Without, algorithmic tools at least, or even possibly endogenizing the norms in the algorithms themselves. And so now there's, more than one conference these days conferences that have cropped up. Here's just one, the unfortunately named FAT ML conference, which is, I don't know what people think when they do these things, and then furthermore, like they actually called it FAT ML from this, like they didn't like call it the whole thing and then somebody pointed out, hey, the acronym for this is FAT ML. They actually started calling it that from the beginning. But anyway, but it's an interesting conference, and it, I've been to I think almost all of them. The fourth one was at NYU last fall, and the first one was a NIP, a workshop at one of the main machine learning conferences, and it was basically like 15 theoreticians talking to each other. And the one last year at NYU was oversubscribed. It had about 300 attendees, and I would say at least a third to a half of them were non-technical people from regulatory agencies, from companies and the like, and it was great. And so, I'm just highlighting here that, the concerns are all of the ones in this audience, but to try to address them with computationally rigorous methods. And let me stop there and take any questions or comments. Thank you.
So yeah, we got time for a couple of questions, probably only about 5 minutes, so quickly. So who's got the microphones? Let's see, Nick here. All right, you pick, and then we have probably time for probably 2 or 3. Yeah, you want to just do it down here? Yeah.
Is this on? Yeah, okay. Hi, Michael. Thank
Hello.
you. Thanks for the talk. That was fantastic. I just have a kind of a clarification question about the work on fairness gerrymandering. I'm just
Yeah.
trying to understand the context in which that problem would arise. I know you mentioned Facebook's hate speech policy, but the assumption is that in order to continue to discriminate, that the regulated party would purposefully is that
So
the assumption?
So I kind of gave the artificial example of the evil country club owner, but let me say something perhaps much more directly relevant. Suppose you give me a traditional statistical definition of fairness, like equality, some data set of decisions that have been made, like XY data, in which we gave this person a loan and they repaid it, and we gave this person a loan and they didn't repay it, and the people are represented by like a vector of attributes, right? It's like their credit history, all these sorts of things. And suppose you tell me okay, look. You can go ahead and use this data set to build a model that predicts loan repayment, but I want your false rejection rate on black people and white people to be the same, okay? So you give me that objective function, and I'm a good machine learning person that minimizes predictive accuracy subject to the fairness constraint you gave me. This is like a classic constrained optimization problem, okay? I have an objective that I'm minimizing subject to constraints. So I'm gonna do that, and what I promise you will happen is that there will be some subgroup of the group that you were trying to predict with respect to false negative rates, okay? And so you can say, I'm okay with that. It's okay with me that I was protecting black people and discriminating against black women. That would be one of the, and what we're asking for is no, that's not okay either.
I see. So the argument is that this is just maybe inherent in the model, not a result of a nefarious actor.
No, yeah, it's just again, one of these things, if you don't put it in your machine learning objective, you shouldn't expect it to be there. And in general, we find that on actual data sets where fairness is a concern, if you do exactly the experiment I described, you will get the outcome that I described.
Tom Keenan, University of Calgary. Isn't it inevitable, if you have enough data with that game approach, which I love, that about people with curly hair, something that's irrelevant, because the algorithm ultimately, with enough data, will converge to find anything, right? So do you have to then have a human intervention to say, yeah, but I don't care about that?
One controls for this sort of, the cure for this is kind of independent of sort of fairness concerns, because I think you're talking about, if I do this long enough, won't my model find some incredibly complex Baroque thing that's actually not real? And so, this is. Then I think I misunderstand the question.
So let's pick something that's a red hair.
Okay.
And the model finds this, and when the model finds this and winds up cooking that into it, and somebody at some point is going to earrings, well, that might be something that we do care about. So it strikes me that there has to be a man-machine component, human-machine component here.
Okay, just to be clear,
Yeah.
I'm not proposing that the algorithm decide what the protected attributes are, okay? That's for the humans to decide.
But it will
okay?
find them, right?
But decided that, race and gender should be protected, for instance. Don't we also want combinations of race and gender to be protected? If I want to protect black people and women, don't I also specifically want to protect black women? Now, if you don't care about if it's okay to discriminate. Just to be clear here, like, you're right that eventually look at a fine-grained enough level, because some people get loans and some people don't get loans. And so you can always find some, like the DNA of the person that you incorrectly rejected a loan to is a unique fingerprint for that person. And so, yes, I discriminate. So it's important that, right? Like, we don't want to care about, and by the way, in the algorithm that I described to you, that's explicitly part of the process, right? We sort of want to protect groups that are combinations of the protected attributes, or probability or density in the population. And so we're not looking for sort of arbitrary Baroque combinations, I think.
Let's take one more, because we don't want to go too far off schedule.
So, question in terms of, so if you're embedding these social norms into the algorithm itself, and you're doing it by human selection of parameters we care about, how easy or difficult it is for those to move on with times. So one is, it gives tremendous amount of control over the people who are choosing the categories we care about. And also, but how difficult or easy is it to change, if you're embedding the norms into it? Social norms change over time, and how easy or difficult is it to then adapt these tools accordingly?
It depends on the level at which you're asking that, because if you're asking me at an institutional level, like, if as a society we tell companies that, this is the notion of fairness that you need to meet, and you then try to change that, like, how long that takes I think all of you can answer that better than I. But at a technical level, it's trivial, right? Like, it's just sort of computation time. Like, if you tell me on that, now there's another attribute we want to protect, for instance, okay?
So that we'll have to have an explicitly. So
then we would basically, kind of incorporate that new attribute into the algorithm, and we might need to, like, rerun it on the historical data again. Okay. But this is just CPU time.
That would be something you have to explicitly run.
You would have to explicitly do it. And by the way, like, I think this is a good thing. Like, I'm just, lest people, think otherwise. In general, me and people like me don't think that machines should be in the business of deciding what the notion of fairness is, what the protected groups should be. That should always be in the domains of human beings. But, about committing to notions of fairness and being explicit about them, and then figuring out how to, implement them from a design and engineering standpoint.
All right, unfortunately, we got to wrap up.
Thank
Thanks
you
so much for a great
Thank
talk.
you. Like me don't think that machines should be in the business of deciding what the notion of fairness is, what the protected groups should be. That should always be in the domains of human beings. But, about committing to notions of fairness and being explicit about them, and then figuring out how to, implement them from a design and engineering standpoint.
All right, unfortunately, we got to wrap up.
Thank
Thanks
you.
so much for a great
Thank
talk.
you.